start problem number 11, the first problem of this chapter, that is kinetic theory of gases and radiation. Let us start. Let us read this. Calculate the ratio of mean square speeds of the molecule of the gas at 30 Kelvin and 120 Kelvin. So about to take the ratio of these two. How to get this ratio? See, here it is. The question is before you. Once again, calculate the ratio of mean square speeds of molecules of the gases at 30 Kelvin and 120 Kelvin. Here T1 and T2 it is given, and accordingly I am going to write this. Here data for the problem number 11. Here it is the data before you. What it is given? T1 is equal to 30 Kelvin, and what about the T2? It is 120 Kelvin. Let us check. Yes, it is correct one. Now T1 is equal to 30 Kelvin and T2 is equal to 120 Kelvin. So we need to write this here. C1 square, C1 bar square, we can term it as a root mean square velocity. The ratio of that one we need to calculate, C2 bar square. So this is the question mark, and we know the general formula. Here it is the formula for that one. The formula is as follows. Here it is the formula before you, that is C bar is equal to under root of 3 R T upon M. This M we know very well. It is a molecular, we say, weight of that body or molecular mass of that body. R is the gas constant. T is the temperature, which is already given. So I am going to write that here C bar square is equal to under root of, or sorry, here it is under root, it is discarded. So accordingly, here it is 3 R T upon M. So accordingly, this is the general formula, and we are going to express this in terms of C1 and C2, that is T1 and T2 also. Here it is the formula, first formula before you, that is C1 bar square is equal to 3 R T1 upon M. Give it as the equation number 1. And C2 bar square is equal to 3 R T2 upon M. This is equation number 2. So seems to be knowing all that, C1 bar, C2 bar, we are going to divide both the equations. Dividing equation 1 by 2. And obviously from C1 bar square upon C2 bar square is equal to, here I am going to write 3R T1 upon M. And what about this? 3R T2 upon M. For the similar kind of molecule, so seems to be considering this. What are the cancellation factor? 3, R, M. Okay, all these get cancelled. Only remaining is, here it is T1 upon T2. What about the T1? Already is given 30 upon 120. So it is 1 by 4. So our answer, C1 bar square as to C2 bar square is equal to 1 as to 4. This is your answer. Now the problem number 12 before you. Two vessels. Here it is. Two vessels A and B are filled with the same gas. See, same gas, where volume, temperature and pressure in vessel A is twice the volume, temperature and pressure in vessel B. Calculate the ratio of number of molecules of the gas in vessel A to the vessel B. So let us get that. Very simple. Already we have going to start this number 12. Here it is 12. Data before you. That is pressure is PA is equal to twice the PB. As per the data it is given. Same gas it is taken, but the pressure at A is equal to twice that of B. So PA, PB, VA, VB, here it is twice the VB, and what about the temperature? TA is equal to twice the TB. So accordingly, here it is, I need to calculate NA upon NB. So how to get this? Question mark. This is nothing but a number of molecules in A, number of molecules in B. See, here I am going to take one formula for that one. The formula is as follows. Here it is the formula which is given, that PV for the ideal gas PV is equal to nRT. What about this number of moles of a gases? Number of moles of a gases and number of gases. It is different. So we are about to get this. Don't get confused in between these two. Number of moles of gases. Here it is number of molecules. So how to get that? Let us see. So N is equal to how much? Here it is, N is equal to PV upon RT. PV upon RT. So accordingly, I am going to write NA is equal to PA upon VA divided by R into TA, and accordingly NB is equal to PB into VB upon R into TB. So accordingly, I am going to divide that one. NA upon NB is equal to, here instead of writing that one, I am going to write somewhat bigger. So NA upon NB is equal to PA into VA upon R into TA divided by PB into VB upon R into TB. So accordingly, I am going to substitute all that values. So going to be substitute 2PA into 2PB upon R into TB, and here I am going to write 2PB into VB upon R into TB. Similar factor get cancelled. Here it is PB. Okay. Here it is VB. Instead of that one, it is VB, not the PB. Okay. Already we have written this one. Instead of that one, PB. So here it is. Here it is also PB. See here, PA is equal to twice the PB. VA is equal to twice the VB, and here it is R into TA means TA is equal to twice the TB. All the values it is substituted. Okay, nothing we are going to write here. So similar factor get cancelled. PB PB, VB VB, TB TB, and here it is R get cancelled. What about these two? 2 cancels with these 2. Okay, so the answer before you, it is 2 by 1. But it is the final answer? No, not at all. It is the final answer. That is NA upon NB is equal to 2 upon 1. But actually, number of molecules in a container or in a vessel A to the vessel B can be calculated NA upon Avogadro's number, NAVG Avogadro's number, divided by NB upon N Avogadro's number. This will give us a number of, we say, molecules inside the vessel A and inside the vessel B. So accordingly, the similar term get cancelled. Avogadro's number get cancelled, which is equal to NA upon NB, and which is equal to this much, means it is equal to 2 by 1. This is our answer. I am going to write that NA upon NB is equal to 2 as to 1, or I am going to also write NA as to NB is equal to 2 as to 1. This is our answer. Here it is the problem number 13 before you. Let us start with this 13. So accordingly, the problem number 13 is before you. A gas in a cylinder is at a pressure P, is at a pressure P, if the masses of all the molecules are made up of one third of their original value. See, if the masses of all the molecules are made up of one third of their molecules original value and their speeds are doubled, then find out the resultant pressure in terms of pressure means original pressure. So get the value of final pressure. But before that one, what exactly the value which are given that I need to write here. The initial pressure is a P1 and accordingly I'm going to write the data. So data before you, the masses M2 is equal to M1 upon 3, one third of final mass of gases is one third of its original. And what about the next? That what it is given, the speeds are doubled. That means I'm going to consider C is the speed and accordingly C2 is equal to twice the C1 means double, and I'm going to write this bar. Why? Root mean square velocity of a gaseous molecule. So accordingly we know the formula for that one. The formula which is given by here, the formula is P is equal to one third of M N C bar square upon V. V is the volume, M is the mass, N number of molecules, C bar square, C RMS velocity, root mean square velocity, V volume, P pressure. So accordingly P1 is equal to one third of M N C bar square upon V, and similarly P2 is equal to one third of M. Here instead of writing the for P1 I am going to write M1. Okay, volume is same, so here only C1 M1 and here it is M2 N into C2 bar square upon V. So accordingly I am going to calculate the P2. So P2 upon P1 is equal to, going to substitute all the values. Here it is P2 one third of, I am going to substitute M2 M1 upon 3, M1 upon 3, N into C2 whole square means a 4 C2 bar square. Okay, sorry, here it is C1 because C2 is equal to 4 times C1. Okay, so here what about this? As it is I am going to write P1 one third of M1 into N into C1 bar square upon V. So what are the terms get cancelled? One third get cancelled, N get cancelled, C1 bar get cancelled. So the remaining factor is 4 by 3. Means P2 is equal to 4 by 3 times P1, and this is your answer. That how much is the pressure of second? That is 4 by 3 times the original pressure. Here it is a problem number 14 before you. Here I want to show something. Show that a root mean velocity of an oxygen molecule is under root of 2 times that of sulfur dioxide molecule at STP, that is standard temperature pressure. How to get that? We know the RMS velocity formula, and before that I am going to write the molecular masses of oxygen and sulfur dioxide, and accordingly I am going to give the answer for this one, that is 14. Here it is the problem number 14. Data before you. Data, molecular mass of oxygen, that is O2, is equal to 32. And what about the sulfur dioxide? Molecular mass of sulfur dioxide is equal to 64. And I am going to, accordingly I am going to obtain the relation. Show that, one second, show that RMS velocity of an oxygen molecule is RMS velocity C RMS of oxygen or I am going to write here oxygen is equal to under root of 2 times CRMS of SO2 molecule, or I am going to write in short, that is O2, oxygen. So I am going to show this. Actually, I am going to show this. How to get this? Very simple. I know very well that formula regarding the RMS velocity we have already derived. Here it is. So CRMS, or instead of that one C bar I am going to write, but here it is CRMS is equal to CRMS for the oxygen. Here C bar for the oxygen, here it is oxygen root mean square velocity for the oxygen O2, it is equal to under root of, or the general formula, instead of that one I am going to write the general formula, that is CRMS is equal to under root of 3 RT upon M. So C bar oxygen molecule is equal to here 3 RT upon molecular weight of oxygen. Similarly, C bar SO2, that means RMS velocity for the sulfur dioxide molecule, it is given by under root of 3 RT upon M SO2. So accordingly, if I am going to substitute all that value and divide, see here is C bar oxygen divided by C bar SO2 sulfur dioxide. I am going to divide it. Accordingly, the oxygen, that is 3 RT upon MO2 upon under root of, here it is 3 RT upon MSO2, which is given by, all other factors get cancelled, 3 RTM, only the remaining factor it is. I am going to take inside the square root MSO2, directly inside the square root I am going to write MO2. Obviously it is under root of 64 upon 32, it is equal to under root of 2. So accordingly, C bar O2 is equal to under root of 2. This is get divided to this, and here C, okay, RMS velocity for sulfur dioxide. Hence the proof that CRMS of oxygen is equal to under root of 2 times CRMS of sulfur dioxide. Here's the problem number 15 before you. Let us read out the problem. At what temperature will the oxygen molecule have the same root mean square velocity as a helium molecule at ESTP? See, helium molecule at ESTP. So question mark means at what temperature? We need to calculate the temperature for the oxygen where helium is kept at standard temperature pressure, ESTP. The molecular mass given, the molecular mass of oxygen and helium is 32 and 4 respectively. So accordingly I need to calculate that. Very simple it is. Once again I am going to utilize the same formula, but for the 15 I have the data before you. Data, temperature for the oxygen I need to calculate TO2, question mark, but helium, temperature for the helium is 273 Kelvin for ESTP. At ESTP means a standard temperature pressure, standard temperature pressure. And accordingly I am not going to write these dots because we know very well. I am going to write ENTP, ESTP just like that. So here what we need to calculate and what it is given, the molecular mass of oxygen already we know very well, that is this is 32, and molecular it is given, molecular weight of molecular mass of helium it is given by 4, and accordingly I am going to calculate the T. So very simple. We know the general formula, that is C RMS is equal to under root of 3 R T upon M. So accordingly, I am going to write one by one. That is CO2, CRMS for the O2, which is given by under root of, here it is oxygen, 3 R T O2 upon molecular weight of oxygen MO2. Similarly, for the helium, CRMS for the helium, which is given by under root of 3 R T helium upon M helium. So I need to get this answer. So how to get this answer for this? If their RMS velocities are equal, once again, at what temperature will the oxygen molecule have the same RMS speed? Means at what temperature these two velocities are same, means we need to equate both. So accordingly, C helium or C oxygen is equal to C helium. So going to be substitute all that values. Here it is under root of C oxygen under root of 3 R T O2 upon MO2, and which is equal to under root of, here it is 3 R T helium molecule and molecular weight of helium, molecular mass of helium. So accordingly the similar terms get cancelled. So substitute all that value, get the answer. So accordingly, squaring both the sides, TO2 upon MO2 is equal to THE upon MHE. So TO2 is equal to THE upon MHE into MO2. Going to substitute, and after substitution, here it is the answer before you, that is TO2 is equal to temperature of helium, that is 273, and accordingly molecular mass of helium is equal to 4, and here in multiplication we have the molecular, that is mass of oxygen, that is 32. So after calculation we are about to get the answer for the TO2, that is 2184 Kelvin. This is the answer. So here it is the final, we say, and further we are going to take 16, 17, 18, 19, 20, up to 20 in the next session. Thank you.